Okay, in the last class we are discussing about the modes of 8254. So we have discussed the first three modes: mode 0, which is interrupt on terminal count; mode 1, programmable one shot; and mode 2, rate generator. So next one is mode 3. Mode 3 is square wave generator. We can generate the square wave using 8254. In earlier lectures we have discussed about the square wave generation using software also. You can using 8255. But the difference is, as I have told in the last lecture also, so using 8254 we can generate the accurate delays. If you want to generate a square wave with 1 kHz, if I use 8254 the accuracy will be more when compared with the generation of the square wave using any other technique such as 8255 and all. Okay. So in this square wave generation, after the mode set, once the mode is set by using that control load register, the counter is loaded with a count of n. So once the mode is set, the counter is loaded with count n. Then once the count is loaded into this counter, the out signal of this particular counter, counter is having one out signal. Out signal goes high for n by 2 clock cycles and low for the remaining n by 2 clock cycles, and the same process will repeats. This is the case if n is even. N can be odd also. So in case of n odd, the out signal goes high for n plus 1 by 2 clock cycles, and low for the remaining, which will be n minus 1 by 2. And the gate signal will be kept high. So these are the different points related to mode 3. So if I take the waveforms, if I take the clock waveform here, this is clock of any particular counter. You have 3 counters, you can use any of these counters, you can program in mode 3. With respect to this clock, how this output will vary, out signal, for both the cases n is even as well as n is odd. High signal means gate signal I am not showing, which will be high. This is clock signal. Then the out signal will be high for n by 2 clock cycles and low for n by 2 clock cycles in case of n is even, whereas in case of n is odd, high for n plus 1 by 2 cycles and low for n minus 1 by 2 cycles. First I will draw for high, n is equal to even. So we know that the change which occurs at the negative edge of the clock. As I have told, there are 3 counters, 16-bit presettable counters, down counters, which operates on negative edge. Suppose if I take out signal for n is equal to say 4, even number, then this will be on for 2 signals, this will be on here 1 and 2, then off for 2 signals, the same thing will repeats. This is out signal if n is equal to 4. This is if I load n with 4. This is 1, 2, 3, 4 or 0, 1, 2, 3. Out in case of n is equal to 5, which is odd. So, for n is equal to 5, what is n plus 1 by 2? N plus 1 by 2 is 6 plus 1 by 2 is 3. N minus 1 by 2 is 2. So, 3 plus 2 becomes 5. So, this out signal will be high for 3 clock signals and low for 2 clock signals. One, 2, 3 high, then low for 2 clock signals. Then again high for 3 clock signals, so on. This is for n plus 1 by 2, which is in this case 3. This is n minus 1 by 2, which is 2 in this case. This is 1 clock signal, 2 clock signals, 3, and this will be 1 clock signal, then 2 clock signals. This is 2 clock signals. It will go to low up to 2nd clock signal, then high. So, this is about the mode 3 of 8254. Okay. So, if I write a program, let us take an example. Generate a square wave with a frequency of 1 kilohertz using 8254. Assume that the clock frequency of 8254 is 1.5 megahertz. As I have told in the last class, the clock frequency of 8254 can vary from DC to 10 megahertz. Here I am considering 1.5 megahertz. So, write what is the solution for this problem. I have to generate 1 kilohertz signal. So, frequency of the signal that is to be generated is 1 kilohertz. Implies time period is 1 millisecond, right. So, the clock frequency of 8254, this is clock, you can call CLK. Frequency of 8254 is 1.5 megahertz. Implies what is time period of 8254 clock is 1 over 1.5 into 10 raised to the power of 6, this many seconds. Okay. So, in order to generate the square wave using this 8254 in mode 3, so we have to load this counter with appropriate value, so that if n value is even number, it will be on for n by 2 clock cycles, off for n by 2 clock cycles. So, how to find out the n value? So, what should be the value of n to produce this frequency of 1 kilohertz square wave if I connect that out signal to the CRO. Okay. So, for that, in order to find out the n value, capital N value, one clock cycle of the clock is equivalent to 1 millisecond. One clock cycle is equal to 1 millisecond duration. Then what is the duration that we want? We want a duration of 1 by 1.5 into 10 raised to the power of 6. For this seconds, how many clocks we require? That is the n value. Okay. So, this will be the number of clock cycles n will be 1 millisecond divided by 1 by 1.5 into 10 raised to the power of 6. This will equal to 1.5 into 10 to the power of 6 into millis 10 raised to the power of minus 3. So, this is equal to 1500. So, if I load this n value with 1500, if I take the decimal, so I have to operate in as a BCD counter. Then we can generate a square wave with a frequency of 1 millisecond at the out signal. Okay. So, in order to load this value, what will be the program? Program for this one will be move AL comma, what should be the control word? Because I am using as BCD counter and I am using in mode 3 and count is 16 bit. Okay. So, if I form this control word register, this last bit is 1 for BCD counting, next 2 positions are, next 3 are for mode selection. So, mode 3 means 0 1 1, next 2 are RL1 RL0, because you have to load a 16 bit number BCD number. So, this will be 1 1, 0 0 is latching, 0 1 is lower order 8 bits, 1 0 is higher order 8 bits, 1 1 is 16 bit. In that first it will load lower order 8 bits, then it will load higher order 8 bits, and this is select counter. I can use any counter. Okay. If I use say counter 0 0 0, this will be 3 7 H. Out, the address of the control register is 03H for the interface connection that we have shown in the earlier class. AL, this is mode set. After that we have to load this count value onto the counter 0, because here you have selected counter 0. Okay. For that you take the lower order values of the count into AL 00H, then out onto counter 0 whose address is 00H comma AL. Counter 0 value is address is 00, counter 1 is 01, counter 2 is 02 and control word is 03 for the connections that I have shown in the earlier lecture. Then you load move AL comma, the higher order 8 bits of the count is 15, 15 out 00H comma AL. Here we will give 15 because you have set this as a BCD counter. 15 will be not be taken as hexadecimal, it will be taken as decimal. Okay. Now we have loaded this, so we have to just jump here itself. So if you execute this program and if I connect this 8254 out 0, this is out 0 because I have used this counter 0 out 0 to CRO. We can observe a square wave with a precise accurate frequency of 1 kilohertz. This you have to connect to positive terminal negative terminal of this has to be connected to the ground signal of 8254. This is how you can generate square wave with a accurate time delays, accurate frequencies. This is about mode 3. The next mode is mode 4, software triggered strobe, mode 4. Software triggered strobe. So, in this case also gate signal will be kept high. After the mode set, we have to load the count value onto the counter. These 2 points are same as that of the previous mode. Okay. Once the count is loaded into the counter, then what happens is this out signal will become high for n number of clock cycles, then it will go to low for 1 clock cycle, that will act as a stop signal, then again it will go to high. These are the waveforms for mode 4. So, if you observe the waveforms, the operation will be understood. This is clock signal. If I take same n is equal to 4, this is clock, I can use any of the counters, right bar, this is right bar signal. I am assuming n is equal to 4. Once this n value is loaded into the counter, from the next negative edge onwards, this is the next negative edge. This is negative edge. The out signal remains high for n clock cycles and then goes low for 1 clock cycle. So, this will be initially high only. So, from here this is 1 clock cycle, 2 clock cycles, 3 clock cycles, 4 clock cycles, then it will go to low for 1 clock cycle, then again it will become high. This is 3, 2, 1, 0, then it will be high for 1 clock cycle, this is out. So, why the name software triggered strobe is this signal can be used as a strobe signal. In many applications, okay. And why this is software triggered? The count is going to trigger the strobe. Okay. Whatever the count that we are going to load here, this is going to act as a trigger for this strobe. That is why the name software triggered strobe. And we have the last mode, which is hardware triggered. Instead of this count, we can use the gate signal to trigger the strobe. So, gate signal is a hardware pin, hardware signal, because there is a pin corresponding to gate. So, the operation is exactly same, except for that here instead of using this count to trigger the strobe, in mode 5 we are going to use gate to trigger the strobe. So, the last mode is mode 5, hardware triggered strobe. Mode 5 is hardware triggered strobe. Here also after mode set, you have to load the n value onto the counter. Then after loading the count, if this high gate signal goes low to high transition, then this out signal will count for n clock signals, means it remains high for n clock signals, then goes low for 1 clock signal, and the same process will be repeated. This is clock signal and this is write bar signal. We have to give the count. Say n is equal to 4 only. Then gate signal, which will act as a trigger signal here. Has to be given as transition from low to high. Then it will remain high, after some time again it will go to the low. So once this low to high transition is occurred, the next immediate negative edge onwards, this is the negative edge. This occurred here, say, so the next negative edge is this. This can be of any duration. This is third clock signal. This is fourth cycle. So for 4 cycles it will be high, then for 1 cycle it will go slow, similar to the previous mode. This is out, initially high, it will remain high after the negative edge which follows this low to high transition of gate, then it will remain high, it will remain high only. For n clock signals, for n clock cycles, where n is equal to 4, so 3, 2, 1, 0, then it will goes to low for 1 single clock signal. So this will act as a strobe signal. This is the out. So here, because this strobe will be triggered by this gate signal, gate is a hardware signal, there is a pin corresponding to gate, that is why the name hardware triggered strobe. So once if gate again goes from low to high transition, automatically same n value of 4 will be loaded into the counter, again it will remains high for 4 clock cycles, then it goes to low for 1 single clock cycle, like that the process will repeats. So this is mode 5. Okay. So this strobe signal will be useful whenever you want to connect a slow peripheral with microprocessor. Okay. So this strobe signal will act as a handshaking signal. Handshaking signal is something like, if I want to transfer the data between 2 devices, say microprocessor and peripheral, so initially the signals will be exchanged between these two before the data transfer will take place. Initially the microprocessor will request through this signal to get ready, because normally the peripheral is slow device. Whenever the peripheral is ready, it will send the acknowledgement through this one, acknowledgement signal, that data is ready. After that the data transfer will take place. Okay. Before the actual data transfer, the signals has been exchanged. So these two signals, this signal and this signal are called handshaking signals. Why the name handshaking is, when two persons meet, so they will first shake the hand, after that they will exchange the conservation, whatever this they want to convey the information, that information will be conveyed. Okay. So, that is why the name handshaking signals. So, in such applications where the handshaking signals are required, we can use this strobe signals, either it can be hardware triggered strobe or software triggered strobe. So, this is all about 8254. So, we have discussed about the block diagram of 8254, then we have discussed about the control word register format, the interfacing of 8254 to 8086, then different operating modes of 8254. Okay. So, the next peripheral device is 8259, is called programmable interrupt controller. Programmable interrupt controller. Called PIC. The IC number is 8259. It is exclusive IC 8259, which will act as programmable interrupt controller. First of all, what is the need of this programmable interrupt controller? So, we know that the microprocessor can be interrupted through the device, IO device. This is microprocessor, it can be any microprocessor 8086A. Okay. So, I can connect the different IO devices, we can have a number of IO devices. This is IOs 1, IO 2 and so on. Suppose the number of interrupts of this one is more than or equal to the number of IO devices. Suppose if I have 3 interrupts, of course in 8086 we have 2 interrupts only, I will call otherwise general microprocessor. First I will explain the concept, so I will just call as general microprocessor. Because this 8259 is compatible with 8085, 8086 and some other microprocessors also. Suppose if I have say 4 interrupts and 3 devices, I can nicely connect this IO device to one of the interrupts of this one. This is INT 0 say, INT 1, INT 2, INT 3. So, in this case there is no conflict, there is no conflict because the number of interrupts are more than the number of IO devices. So, when does the problem arises is if you have the number of interrupts less than the number of IO devices. This is the case where the number of interrupts are more than number of IO devices. So, if I take the second case where the number of IOs are more than number of interrupts. Suppose if I have only 2 interrupts and I have say 4 IO devices. Then you have to connect at least 2 IO devices to each interrupt. You have to connect these 2 to the same interrupt. Similarly, you have to connect these 2 to the same interrupt. In that case, you have to assign the priority and you have to resolve the problem. Okay. So, in order to resolve this problem where if the number of interrupts are less than number of IO devices. So, you have to resolve the priority problem and you have to interact with the microprocessor. Okay. There should be some sort of a mediator is required between the IO and microprocessor, which will manage the efficient use of this interrupt system. Okay. So, that manager is this 8259. 8259 will act as overall manager between the IOs and microprocessor. Okay. So, this will perform the various tasks like assigning the priority to the IO devices. Okay. The one with highest priority will be served first, after that remaining will be kept pending. Okay. So, all these operations will be performed by this 8259. This 8259 will act as the overall manager between the microprocessor and IO devices. Here 8259 is not required because number of IOs are less than number of interrupts. Whereas in the second case 8259 is required to resolve this problem of conflict between the different IO devices. So, what is the first block diagram of 8259? So, how this will resolve the problem? So, we will discuss in the next slide. So, if we come for this block diagram of 8259, this is a 28 pin IC. Okay. The different signals that are available on this 8259 are shown on this architectural diagram. So, if you consider the architectural diagram of 8259, there will be some internal bus, this is internal bus. So, which will be used to communicate between the different blocks of 8259. So, the main important blocks are, there is some control logic, then we have, for this control logic we have INT A bar and INT R. There are two signals which is called INT. I will explain the functions of all these signals in detail. This is INT A bar. INT A bar is the active low signal, so I have placed a bubble here. Normally a bubble represents active low signal. Okay. And then we have interrupt request register, through which each interrupt can be used to serve 8 IO devices. There is one block called interrupt. This block is interrupt request register, IRR. I will write the abbreviations here. IRR is interrupt request register. I will explain the functions of this. This will be having 8 signals, IR0 to IR7. So, each interrupt can be connected to 8 IO devices through this IRR, because if all these interrupts occur simultaneously, then you should have some circuitry to resolve the priority of these interrupts. So, there is a priority resolver. Priority resolver. Then we have in service register, which keeps the record of the serviced interrupts. In service recorder register, ISR is in service register. So, this will be connected to the internal bus. So, this is the connection between the control logic and these 3 blocks. Then we have interrupt mask register. So, you have to mask some interrupts whenever more than one interrupt request the use of this interrupt of 8086 or any microprocessor. There is an interrupt mask register. Interrupt mask register. So, there are total now here 8 signals, here 2 signals, total 10 signals, and we have similar to this 8254, there is a data bus buffer which will be used to transfer this control signals and status signals of 8259 with microprocessor data bus buffer. So, this is 8-bit data bus which has to be connected to the data bus of 8086 D7 to D0. Then we have read write logic which is also similar to 8254, read write logic. Here we will be having chip select signal, A0 signal, this is chip select signal, read bar signal, write bar signal. These are common with 8254 also. But in 8254 we have A1 and A0, whereas here we have only A0. A0 in connection with read bar, write bar signal will be used to select the different registers inside the 8259. There will be cascade buffer. We can cascade, one of the feature of this 8259 is we can cascade 3 8259s together. Cascade buffer, comparator, so this is also having 3 signals. This is having 3 signals. CAS0, CAS1, CAS2. Then we have one active low signal which is called as SP/enable. These are 2 active low signals. So, SP stands for slave priority, EN stands for enable buffer. So, there are total 28 signals. There are 8 signals here. and this 8 signals here, 16 signals, then 2 signals here, 18, 19, 20, 21, 22, 23, 24, 25, 26, and there are 2 signals VCC and ground. This is a 8259 is a 28 pin IC. So, if you come for the functions of different signals, so whenever a IO device which is connected to one of the interrupts of one of these lines of this IRR register. So, this will be connected to one of the IO device, this will be connected to one of the IO device, this will be connected to one of the IO device. So, at a time 8 IO devices can be connected through these lines. So, what this IPR will do is, so whenever the request comes, so it will store, it will give this as highest priority. In case of normal process, and there is one process called rotating priority, where we can program the priority of IR0 to IR7. So, in the normal case, this is highest priority and this is lowest priority. So, the signals that will be received through this IR0 to IR7 will be resolved, it will be assigned some priority, then the one which has to be processed is given to the ISR. So, how does this interrupt will be processed? So, correspond to each interrupt will be having one interrupt service subroutine. So, whenever the microprocessor is interrupted through this will be connected to the microprocessor. So, whenever the microprocessor receives this interrupt, the microprocessor control will transfer to the interrupt service subroutine. Okay. So, when how does this interrupt for the microprocessor will be enabled? So, based on this 8 requests, this will resolve this problem, and the one with highest priority will be considered, and that will be stored in ISR. Then after assigning this highest priority, this 8259, this complete 8259 will request the microprocessor through this signal INT signal for the use of that interrupt of 8086. Once the microprocessor is ready to accept this interrupt, it will acknowledge through INTA bar. Once this INTA bar becomes 0, so the interrupt branch address of that particular interrupt will be placed onto the data bus. So, the microprocessor control will goes to that address and it will perform whatever the task that is required for that particular interrupt. Then the last instruction of the interrupt service subroutine is I return, interrupt return, it will come back. Then the device with this next priority will be recognized and the corresponding address will be generated by this ISR, and that will be placed onto the data bus. The microprocessor control will goes to the that particular service subroutine and it will resolve. Okay. So, in that way we can process 8 IO devices if I use single 8259, whereas as I have told here, cascading of 8259 is also possible. If I cascade 3 8259s, then what happens is, corresponding to each 8259 8 devices we can control. Okay. So, using these 3 we can have 8 combinations. So, we have 3 bits means 8 combinations and corresponding to each combination we can have 8 devices. So, totally we can have 8 into 8, 64 IO devices can be connected in cascade mode. IO devices can be connected if I use this cascade mode. Because of these 3 bits, 8 combinations, and in each combination we have 8 different signals. So, total 8 into 8, 64 IO devices can be connected to this 8254. And this read bar, so whenever this microprocessor want to read the status of 8259 registers, so this read bar will be 0. Similarly, write bar means the microprocessor will write something. So, A0 in connection with this read bar and write bar will be used to select the various registers. So, these are the main functions of this. There is a slave processor mode. So, this will be used in cascading modes. So, enable buffer. So, how this 8259 will be cascaded we will discuss later. Okay. So, these signals are basically cascading signals, and this is also used for, because this is connected to cascade control, this SP bar by N bar. So, this is about the overall function of 8259. Similar to 8254, 8255, here also we have some control registers. By programming the control registers, we can control the operations between 8259 and 8086. So, the details of the control registers and how this control register can be programmed to service the IO requests we will discuss in the next lecture. Thank you.